The chairperson is Astrid Brun. So the session is in your hand, please.
Okay. Thank you, Daiso. Thank you, Professor Fujita and Professor Takara. So the procedure is as follows. We'll have two talks in session one, two talks of each 30 minutes, and then we'll have 30 minutes of discussion. The first talk will be given by Christian Escauriaza, and the title of his talk is Computational Models of Flow, Sediment Transport, and Morphodynamics. Thank you.
Thank you, Astrid. Well, before starting, I wanted to say thank you. Thank you for the invitation first, and also thank you to the organizing committee. It's quite an honor being here. This talk is exclusively my responsibility, even though the excellent chapter was written with Chris and Vaughn. Probably this chapter was started like 6 years ago when I was at the St. Anthony Falls lab, and we used to have these long discussions about models. And since I was at the time working with Fotis, and I'm more of a CFD guy, so we had a lot of discussions, and we agreed and disagreed in many things, and so that actually motivated this chapter. When I was preparing this presentation, actually, I think about this painting by Cézanne. I don't know if you've seen it. It's a painting of Mount Sainte-Victoire by the end of the 19th century. You see, it's representation of nature. I really think that when you create a model and try to understand nature, it's the process for us who like painting is sort of similar to the intellectual process of actually art. And what I like the most is that even though this is very well defined, and you can say that it was a nice day in the south of France and everything, a few days later, years later, he painted this one, which is much more abstracted, thicker strokes, and you don't know if it's day or night. It's very special. So what I think is that when we create a numerical model, somehow the observations are the clues that nature gave us, and the intellectual process to represent nature is some sort of a detective's work, right? There are clues that you have to try to understand and develop a model, and there are many factors, right? Especially turbulence, sediment ecosystems that can even complicate things. So, with respect to the development of the numerical models, we can ask first, what is the best model to describe a fluvial system? It's very common in our area, especially in fluid mechanics, that people believe that it's the more complicated or the more detailed the model it is, it's better, which I think it's not, right? We'll discuss about that later. How we can choose the right modeling approach to understand a fluvial system, and the questions which is part of the conclusion of this talk is, can we combine models to improve our understanding of rivers? So what I'm going to do now is going to go very fast, because I really think that there is a continuous spectrum of models of fluvial systems, but there are some classical approximations that you can actually identify by name and classify them, right? So, first of all, what it's called or is known as reduced complexity model is probably the most simplified of models. It's usually carried out to investigate pattern formations, self-organizations, and this actually is motivated by the classical cellular automata type of models in which you have a discrete two-dimensional plane and you have a set of rules, right? Very simple rules that you can help develop and create emergent behavior. So, as I said before, right, simplified models mainly to investigate pattern formation and self-organization. A set of rules represent the fundamental conservation laws of nature. Most of these models have equations for mass conservation, but have really simplified ways of modeling momentum equations. And they have been really useful to capture many morphological patterns. Probably the most well-known model is Murray and Paola's model of river braiding, right? With just few sets of rules, the models show that the feedback between the topography and a nonlinear sediment transport equation could form these patterns and reproduce many things that are observed in braided rivers. If you go one order of more complexity, we have these diffusion models in which basically you are assuming that erosion or some processes in the landscape can be modeled as diffusive, and you end up with the Exner equation as a nonlinear or linear diffusion equation. These equations also simplify mostly the momentum equation for the flow, assuming that's uniform flow, and you can deduce equations like this. Actually, a couple of days ago, by solving this equation, I developed a model. I'm sorry, this is before. I developed a very simple model, 2 or 3 lines in a code. I think the animation is not working. Oh no, I'll see if I can find the animation outside. No. Okay. What you could have seen, I can show you later in my computer, is with a very simple model you can create. Oops. Okay. Yeah, I know. Okay. With a diffusion model, you can create a drainage network that looks very similar, actually, and it's if you calculate the spectrum, you can see the hill slopes, and the network has a lot of properties that have also been observed in real watersheds. So one order of complexity, of additional complexity, we have the shallow water equations. You probably know all the assumptions that these equations have. In this case, most of the morphodynamic large-scale processes either use the uniform model assumption, or they calculate some sort of backwater equation profile. Then when you have the stresses that are not uniformly distributed in the cross-section, you probably need to use two-dimensional models, especially for problems like rapid flood events. Just to show you a couple again, I hope they work. Yeah. This is a model of actually, this research got recently published at the Water Sources Research. It's just the morphodynamic interaction with the biogeochemical processes that we are studying in the north of Chile. We use a backwater equation just to simulate how the delta advanced in 100 years and how the contaminated sediments with arsenic got deposited in the bottom set. On the other hand, as I said before, if we had a very complex and rapid flood event, I forgot the reference. This paper was published last year in the Journal of Hydraulic Engineering. One of my students developed a model to resolve the two-dimensional Saint-Venant equations with high resolution. We have now incorporated sediments and high concentrations of sediments and bed resistance like this. Well, when the bulk quantities of the flow, like the slope, the sediment size distribution, the discharge are important. The slope, for instance, this type of models work really well when you need a three-dimensional information of the flow. There's no way but simulate turbulence, right? In that case, you need a three-dimensional model. The most basic type of models are the so-called RANS models, Reynolds Average Navier-Stokes, in which you use a statistical decomposition, the Reynolds decomposition, to end up with an equation that contains derivatives of correlations of velocity fluctuations, and you need a statistical turbulence model to represent how this behave. The most common and well-known models are the so-called high isotropic models like K epsilon or K omega, and also all these isotropic models assume that you can represent these correlations of velocity fluctuations in an analogy to the molecular diffusion, in terms of eddy viscosity or turbulent viscosity that you have to calculate somehow, right? So this is very well known, and they work really, really well. The only problem is that more complex Reynolds average model that solve the entire tensor of all the Reynolds tensor, this correlation of velocity fluctuations, are sometimes much more complicated to calculate, and you can ensure really that they will be able to represent issues or flows in which you have high anisotropy, which means like strong separation, helical flows, or specifically when you have turbulence stresses that are different, viewed from a different perspective. So in that way, the higher level of complexity, and here we are dealing with a high computational cost, is go to the so-called large eddy simulations, in which we filter in space the Navier-Stokes equations and try to resolve most of the turbulent cascade. What I have here, I'm sorry I didn't, this is the well-known Kolmogorov spectrum. So here in the bottom you have the wave number, the energy is here. This is non-dimensionalized, so all the experiments show that this is a universal type of behavior. So the scales of turbulence you have to your right dissipate energy. The viscosity is high enough for these scales to dissipate energy. Here you have basically an inertial process in which is the so-called energy cascade, in which larger vortices transfer the kinetic energy to smaller vortices. So in large eddy simulations, even though most of them, and I can go deeper later into this, most of them use the same eddy viscosity approach as in RANS, the space filtering allows us to resolve most of the spectrum. So depending on the resolution of your discretization of the grid, right, you can move this vertical line to the left or to the right of the spectrum. So if you have a very fine grid, you will move this to the right and you will be able to solve most of the turbulent structures in the flow. If you have a coarse grid, you move this line to the left and you are modeling most of your turbulent spectrum. So to explain better, if this is your numerical grid, you cannot see vortices like this. You have to model them. You do see vortices like this. You can resolve them, right? So the finer your grid, the better your resolution, the more you resolve. So one of the biggest problems of LES in terms of computational cost is that they really become really expensive when you want to simulate the boundary layer. You probably know that the boundary layer is populated with these very complex hairpin vortices and have very high frequency events of ejection, sweeps, outward and inward interactions. So resolving this for Reynolds numbers that can be practical or at least give you an idea of what really is happening in a river becomes really expensive. So there are several ways of overcoming this, especially in terms of resolving with LES structures that are not near the bed. So you can either use a wall function, for instance, to represent how the turbulent boundary layer behaves, or you can use hybrid models which combine Reynolds averaging with LES. So you use a Reynolds average as a statistical approach very close to the bed, so you don't have to resolve the coherent structures of the boundary layer, but you can resolve larger scale structures with LES outside of the boundary. So this was part of the investigation we made on the horseshoe vortex system, which is a very well-known vortex to produce erosion and a scour around structures. And since we were able to use this model, this was the first time that we could capture every single aspect that had been observed in experiments in the horseshoe vortex system before. And probably the most detailed of all models is what is so-called the direct numerical simulations. And we resolve all the turbulent spectrum. We go from the largest scales to the smallest scales to the dissipative scales, which are the Kolmogorov length scales, which of course are very expensive. And the only reason they have very large computational costs, you can only reach a small Reynolds number due to this. But it is important, maybe sometimes use it when you want to understand what is the relation of the smallest scales of the turbulence in rivers, right? Just show you one of the simulations that one of my students is carrying out. This is DNS of sediment particles, actually. We are studying intermittency produced by the coherent structures of the boundary layer, and we can resolve, I don't know, 100,000 particles, the trajectory and momentum and of each one of these, coupled with a DNS model resolving up to the Kolmogorov scale to represent the transport of grain by grain. Okay, so when we look at models then as research tools, I would like to emphasize that the most important thing is not the model but the scientific question. So once we understand that, once we know what we want to learn, it's obvious that we can define the equations and the variables to describe the dynamics of the system. And except in LES, I can explain that later, but once we select a model, implicitly or explicitly, we have the non-dimensional parameters, we have the scales for which we have the scope of the model, we have the applicability of the model there, right? So this is very important. So what are models important for? What we can do with them? Used as research tools, they can give us information about pattern formation, for instance, self-organization, dynamics of nonlinear system. We can identify the transitions. We can perform numerical experiments to see how different parameters affect the system and when this dynamical system go through a transition. We can recognize what are the most important in terms of the flow, for instance, the coherent structures of the flow, which of them, which can be small, can have large scale consequences, right? Etc. And one of the things that we do is that once we are able to develop a model, test it, validate the model, we can say that we have captured the most important aspects, and we can use the model then to perform simulations, to perform experimental numerical experiments, right, as I said before, to see how the system behaves under conditions that we cannot measure, for instance, or that we have not tested, different scenarios, right? So the question is it a more detailed model always better? And as I said at the beginning when I started, I think it's not, right? And the second question is there any value identifying and understanding the minimal set of processes that reproduce a phenomenon? So just to show you an example, which is, I think it's a great example. This is the Outdoor Stream Lab at the University of Minnesota. My friend Suku and Fotis performed some simulations there with a very detailed bathymetry. And what I'll show you, and they also use the data measured with ADV in the channel. I hope you can see that. Probably this is the image from their paper. What we have here is that the red line, well, the circles are the ADV measurements. The red line is LES, and the dashed line, that I don't know if you see it, but it's in every picture, it's URANS. It's a K-omega model, right? So by comparing the observations in this case to the simulations, you could say that the Reynolds average approach performed much better, right? It's closer to the simulations. Well, the thing is, when you look at the flow now, the flow is totally different. The topology of the flow they found is totally different, and the RANS simulation has nothing to do with the real flow, right? And why? Well, of course, this is a flow with high curvature. You develop a lot of anisotropic turbulent structures, right, which a isotropic turbulent flow is not capable of resolving, right? So if somebody had performed a 3D simulation saying, oh, this is much better because it's 3D, it's URANS, and they got it totally wrong, right? If you wanted to move one step forward and understand what's really happening with the flow, either you have a very simple model that performs better than RANS, or you perform LES all the way and understand the fine structure of turbulence, right? I think this is a very, very good example of what happens sometimes in this case. Well, how do we choose a good model, and this is something we had a lot of discussions on. First of all, if the objective is understanding self-organization and pattern formation, probably the first thing you can explore is the development of a reduced complexity model. They have shown they have a lot of capabilities of doing that to understand some morphodynamic processes, especially when they have this scale invariance that decouples them from the details of the flow, right? Then, if we have bulk quantities, like I said also when discussing these equations, when bulk quantities like the flow, the slope, the sediment size distribution are the important issues, we probably will have to solve the Saint-Venant equations, the shallow water equations, right? Obviously, if you want to understand the arrival of a flood wave or something like that, probably there's not much information you can get from the finest scale structure of turbulence, right? It doesn't make any sense to perform LES in that case. When the three-dimensional effects of the boundaries and initial conditions affect significantly the system, then you have to go 3D and resolve the turbulence, right? So in these terms, Reynolds average is the most expedient alternative for three-dimensional flows, except when you have an idea that anisotropy might play a fundamental value. And then, while resolving LES or DNS are only justified when you want to understand the relations for the smallest scales possible, right? So this whole idea of choosing a model also make us question what are the future challenges, how the small scale or detailed models, high fidelity models can help us to develop larger scale models that can help us understand the nature, right? So there are a lot of future challenges that I think that we haven't yet addressed in a lot of detail, especially in terms of bed load, for instance. You know that the bed load transport equations at larger scale sometimes they don't perform too well. So how can we use these Lagrangian, very detailed models to inform larger scale models and improve them, right? Then bed form dynamics, now there have been recent advances in that area, or flow over vegetation. Actually, turbulence at the edge, that's one of the topics that is really difficult, and it could be really great to have detailed models that can inform or improve also the relations that exist for larger scales. Free surface, for instance, that's another topic that is very interesting. Contaminant transport, you know, rivers are not impermeable, have not beds, they're impermeable beds, so it's also, hyperrate flow is also an important thing. Just to show you a couple of things, is also the DES simulations, the hybrid simulations I showed you before. Let's see if I can, help us to develop a very advanced model for the bed. We couple the horseshoe vortex resolution with the Exner equation, and this was the first time that a fully three-dimensional model was able to resolve bed forms. We analyzed statistically the bed forms, and they had the same properties that realistic bed forms. And now Ali and Fotis have gone a step further. They have done a full-scale near wall resolving LES to understand how the small-scale structures of turbulence produce these small structures in the bed that develop into ripples in time, with a model that has an immersed boundary method to resolve the boundaries. So to finalize, I would like to finalize with a couple of questions. Can we use this idea of resolving some part of our dynamics and model other part of our dynamics in river systems? It's a good metaphor, turbulence, to understand the methods and to develop new models. So, of course, many morphodynamical systems show self-similarity and scale invariance, just like turbulence. So we can think that it's a great idea, and some things have been done. Probably you know what Chris has done with with his 1D model for braided rivers, in which he performed Reynolds averaging, and you end up with an equation with a lot of correlations also in this case. And also for landscape evolution system, this is Paola Pasalacua's model, in which she used the same concept as LES, trying to model part of the structures to try to come up with a value of erosion across scales. Again, inspired by or with the same idea in which we model turbulent flows. And the second question is, can we develop systematic methods for using detailed models that inform simplified formulations? Which is, what if we take a very basic, let's say, reduced complexity model and keep adding levels of complexity until we capture the dynamics we want to understand? That would be a good idea to say, okay, so these are the parameters, or these are the processes that control the dynamics we are studying. And we can do the other way around, right? Start with a very complicated model, and then start simplifying it and see in which point we are not resolving, or we're not solving what we want to understand. So you would say, can we devise a set of rules for high fidelity simulations that can help us to develop laws or have a better idea of how the same processes looked at a larger scale? I don't know really a question. That's something that I'm working into. I just wanted to show you something that I'm working on right now. I started with some friends studying this surface storage zones in rivers, and we said, okay, let's start from the simplest thing. Let's analyze like a square cavity in a rectangular channel. And we performed some simulations, and it's a very three-dimensional and complex flow that you couldn't imagine. So you have a shear layer, a three-dimensional shear layer, the flow in the cavity due to the curvature developed. They are called Taylor-Girdler type of vortices paired due to a centrifugal instability. Super, very complex, right? And then once we had the simulation and we could compare it with the experiments, we started doing some experiments with contaminants. For instance, we filled the cavity with a contaminant and started seeing how this contaminant exited the flow and ended up in the main channel. So the study of these surface storage zones in rivers is very well known. They are used for stream restoration and many other processes, right? So what you do in general is to use a one-dimensional model for transport, which is just a linear model that is very similar to a diffusive type of model in which your flux is proportional to the gradient of mean concentration, right? First order linear model. So now that we've seen, when we look at the three-dimensional model from a one-dimensional perspective in a large scale, the things look totally different. And now we can perform numerical experiments on this flow and see what is the influence of changing some parameters and so on. So, for instance, for the emptying case, the linear model is the solution of this equation. It's an exponential decay. We have found that the decay is much slower than exponential. So now we are proving into how to model, for instance, this with a non-local fractional process. And just to show you, this is one of the I finished this like a few hours ago. If we model this with a constant exchange parameter in the one-dimensional case, we are trying to look at the three-dimensional thing. The straight line is the exponential decay, and the red line is the fractional model. And it seems that it represents much better the emptying of the contaminant in the cavity. So now we're thinking, how can we use this very detailed model in which we resolve most of the turbulent kinetic energy to improve the one-dimensional thing and try to understand what are the, for instance, temporal dependencies that are created due to these structures seen in a long time. Well, thank you very much, and I'll leave you with this picture, which I like. Thank you.
Thank you, Christian, for this wonderful overview of models of different levels of complexity. I'm sure there will be some questions, but I'm afraid you will have to wait until after the next presentation. The next presentation will be held by Thanos Papanikolaou, and the title of his talk is Boulder Effects on Turbulence and Bedload Transport.
Can we raise this a little bit? Okay. So this is a topic that I have been actually studying for some time, and this remains in my heart, and it is a very fascinating topic. Gravel bed rivers are in many ways control points of what is going on in larger watersheds. So I'm going to talk today how boulders affect turbulence and how the modification of turbulent flow has transfers down to basically bedload predictions, and perhaps try to give you some ideas or share some thoughts and get also some feedback from you about the variability that we see in bedload transport. So one aspect that is very clear and has been documented here by Marwan is when you try to sort of predict bedload rate as function of stress, and you have the power law and things work well, what we call stage 3. When we are dealing with stage 1 and stage 2, there is where things, so to speak, break down. And clearly, people in the literature who have studied this have attributed that breakdown to the fact that you do have microfeatures developing along the top surface of the bed. But in addition to that, there is, and I think Christian mentioned that earlier, there is where intermittency becomes quite important. So where we got the problems is the low intensity type of regime, but the low intensity regime affects in many ways the bed surface structure, and therefore then has implications to the higher intensity. Therefore, this is something that requires some further investigation. So when we do have a very detailed sort of regime diagram for the sand bed rivers, but for the gravel bed rivers, that's not the case. So what I did is I attempted to put some of the dots there where I believe, based on data that we have, we got more data for step and pools. We got more data about riffles, but we have fewer data where those micro surficial structures, what we call clusters, are present. So moving on, when we try to see where boulders, how boulders affect basically what we call the river continuum, then we can see that their effect spans from basically the cascade type of systems all the way pretty much to the riffle pool. And what we have seen actually over the years is that those boulders tend to be like a nice resting areas, like you are driving on the interstate and the incoming material wants to take some rest, and therefore, depending on the conditions, the flow intensity, which dictates the traffic in that river, so in some ways, it's someone can apply principles of traffic theory to the study of grain movement, especially for intermittent flow conditions. And what you see is you see those discrete clusters, as Ian Reed and others have defined it. And then you see also what the Church group has defined it as the reticulate structures, where you have some chains and microfeatures there appearing. And still I call those clusters because you have groups of particles sort of forming. So what are our sort of key hypotheses that have sort of generated the interest here is that we hypothesize that depositional patches and the shape of those depositional patches really reflect that complex interaction between flow and boulders. Boulders and also boulder packing, as we're going to see later on, and also the architecture, that how those boulders are in some ways laid out, do affect, the grain groupings, the clusters. Also, another thing that we're going to explore is the role of relative submergence. And that has been examined very, very much in air flows. That has been viewed in studying sediment transport for aeolian type of systems. But when we deal really with relative submergence in gravel bed rivers, that remains actually less investigated, remains open. There are different types of eddies, and therefore that makes things very exciting in high relative submergence conditions versus the low relative submergence conditions. And those eddies kind of shape up, therefore, the parking lot. And they shape up the resting areas. And as we're going to see distinct differences where those resting areas are in that interstate that I call gravel bed river. And then the genesis of eddies is an outcome of the complex interaction that the previous talk also addressed. So I'm going to give you, and I hope my movie can play here. This is from some experiments some time ago where we had discrete grains placed atop of a flume, and then you saw this is with uniform size particles, so clustering here was not triggered basically by geometric indifferences or differences, I should say, but essentially due to the micro turbulence that we see in those environments. These are very low flow conditions. And then here are the so-called reticulate structures, and the capture there does not do justice because I started from a condition before the initial, but you can see the chains forming of grains over time. And obviously the video speed is accelerated, so things don't happen too fast in a flume bed. But what mentioned earlier is the role of relative submergence. And this is something that I've struggled over the years because I could not explain why on earth during high relative submergence I see the depositional patches being on the down in the wake region. Instead, in the high relative submergence case, in the low relative submergence case, the depositional patterns are in the stoss. So what's going on here? And this is actually from a picture from Chile over a gravel bar in the, I believe it is the Baker River, where you can see again those patches forming on the downstream end. But so you see this all over the place. Now, so what we want to do, what we would like to do here is essentially take those questions that I asked earlier and try to see how we can use the information over the years to be able to develop better predictive tools in gravel bed rivers where boulders are prevalent. And our basis actually has been the work of Elwyn Jaggers, Bill Dietrich's student, that some time ago actually Elwyn looked actually, she said, well, let me really try to understand here how boulders create a narrowing in the cross-sectional area of a river, how much they affect the conveyance in that channel. And then the other thing that she tried to do very well is actually do the partitioning of the stress. Boulders tend to bear a lot of the stress, and therefore the available stress for grain movement, individual grain movement, is reduced. So the question was where the eddies come into the picture here. And step 2 kind of gives you a glimpse where we are going with this talk. Gives you an idea that we would like to actually incorporate not only the the geometric area that the boulders occupy in that river section, but also the average area that the eddies formulate around those boulders, because that area in some ways affects essentially where those parking lots are in that channel. So what are those goals? The first is determine the frictional characteristics around those boulders. The second is identify the coherence of the eddies and determine which eddies are prominent and which of those are washing, out, away. Some of those eddies may be there, but they may not sustain over a period of time. So we are looking for something also that can be useful. We're looking for a hydrodynamic information that can be incorporated into a bed load formula and in a way that is meaningful. The other thing is obviously the partition of the stress into skin and drag. And then we would like to see actually and explore in a more detail how boulders modify that stress that is available to mobilize the grain particles. And then explore ways of how we can incorporate that information into an Exner type of equation, and obviously try to understand the role of intermittency and how lag times developed from those micro features that you see atop the bed surface affect the migration of the material downstream. And let's start here with the frictional characteristics for the 3.5. That's the higher relative submergence. That means the flow depth is 3 times the boulder diameter, the clast diameter. And you can see really for the higher relative submergence condition that the effects of the boulders are pretty much in the vertical and within 1 to about 1.5 boulder diameter, but then the velocity profile beyond that height remains pretty much unchanged. All the points collapse. This is not the case in the low relative submergence, where if we are going to assume that the log law for a moment is valid, you see basically a systematic shift of the velocity profile. That means that the low relative submergence conditions creates essentially conditions that the friction is transitional. So how that translates now to the frictional characteristics around the boulders. And here what we did is we incorporate the boundary layer theory. So essentially we incorporated information that we have, obviously doing the work in the flume, we have the luxury to get detailed measurements with the PIV and so on, and incorporate really the thickness of the boundary layer in our estimation and the momentum thickness in our estimation of the frictional velocity. And we can see clearly that the solid line here is essentially the friction velocity for the approach uniform flow. So this is essentially the square root of square, GHS And so you see clearly here, 0.5 is the peak where it is, 0 is the front of the boulder, 1 is essentially the end of the boulder, and 0.5 is at the crest of the boulder. And what you can see here is definitely a significant, about 5 times at least, increase of the friction velocity right there at the boulder. So clearly that explains why those power laws, which are very useful for the stage 3, as we defined it earlier, why they break down for lower flow conditions, because we have that high variability. Now you see here what is going on in the low relative submergence. Well, you are going to see more in a moment where I'm going to elaborate on this. Now let's put the boulders, the array of boulders now in the cross-sectional area. So far what I discussed was for an individual boulder. Let's put the array also there. If we had boulders with various densities, and what you see here is boulders mimicking, the boulders are those racket balls that they are mounted atop of the flume bed, and what you see is really upstream of the boulder section, and there were about 45 of those. Upstream of those, you can see upstream of that basically black solid line, you see the sand ridge forming. And you can see really that now all of a sudden we're not dealing with localized effects, but we're dealing actually with ridge scale effects. I'm going to explain that in a second. Moving on to how the boulder array velocity profiles, meaning if we have a boulder which is in an array of 45 boulders versus a single boulder, and we compare those identical flow conditions, clearly we see that the single boulder tends to get more of the stress. Instead, when you have 45 boulders, then the forcing obviously gets partition divided to the 45 boulders. And you can see that in the velocity profile, and you can see that better in the shear velocity, where the red line is the friction velocity value along the longitudinal direction for a single boulder found within the boulder array for identical flow conditions with the conditions that we see here with a blue line. So far, to put things into a context, in higher relative submergence conditions, and I've written that last night, so the boulder affects the profile in the vertical only within or about a multiple of the boulder height. So you do have local vertical effects. And that generates some suspicion about modification of turbulence and metastasis of eddies. In the low relative submergence, the boulder affects the whole profile, as we saw. Shifts in roughness create transitional roughness in the boulder vicinity, and does not generate so much excitement about turbulence, at least in the instantaneous sense, but more excitement about the mean flow properties. So what I'm claiming here is mean flow properties may play more important role in the low relative submergence conditions. In both high relative submergence and low relative submergence conditions, boulder arrays have ridge scale effects, and we saw that with the sand ridge developing. Now, all of this, and this is actually a nice image from Joanna Karen, are not easy experiments to perform with a digital particle image velocimetry. And you can see here the recirculation pattern. And this is from our experiments for the low relative submergence condition, where you see, to our surprise, high mean flow values in the wake area. And remember, I've shown to you two contrasting pictures where the depositional patches were in the high relative and low relative submergence condition. In the low relative submergence condition, you did not have any depositional patches in the wake area because you got flow shooting through, as you see here and you're going to see here in a second. So looking now, switching gears and looking at the vortex topology for the high relative submergence condition. What we see is a much more complex picture. Christian showed to you earlier a bridge pier and the cylinder, and I will tell you that's a very tough thing to do. But when you are dealing numerically or experimentally with a spherical type of shape object, which is truly a three-dimensional object, you get some funny business going on. So a very tough experiments. So what you see here is essentially four types of vortex topologies. The tip vortices that have been reported before, what we call the inner vortices, and I'm going to explain that in a sec. We have the horseshoe vortex, but the horseshoe vortex, to our surprise, was not so strong as we expected. And then what we call the inboard vortices, and those are our own terminology. So let us see here. We have the tip vortex or arch vortex coming from the top. We got the inner vortices, and the inner vortices we believe to be the outcome of the complex interaction between the flow running along the flanks, rushing through the flanks of the sphere, the side of the sphere, and also from the interaction with the hypereic flow. And you do have a jet forming right here as the flow rushes through. And the tilting of that red vortex here, the inner vortex, can change depending obviously on the differential or the shear, how strong is that shear or how weak it is. And then you have the trailing vortex, which we believe to be the outcome of the interaction of the inner and inboard vortices. So this is actually from an LES simulation where kind of you can see that tornado effect type of vortex. I mentioned the flow coming from the porous bed, the hypereic flow, and then the jet coming from the side and creating that helical type of motion that can be very violent and therefore can have effects on the depositional patterns. Moving now to the low relative submergence condition, here things, as I gave you sort of an idea earlier, are less spectacular when it comes to turbulent flow structures. What we have is von Karman vortices, and mainly those are on the lower end of the flow, and we speculate those to be the von Karman vortices based on the wake parameter definition there. So where we are going, and here is a map of the vortex typology. So where we're going with that, what we're trying to see is how much area those vortices occupy. Remember, we want to sort of go back to that bed-load, simple bed-load formula, simple but very brilliant in my mind, and incorporate the information, correct the prediction of that formula by incorporating essentially the area that those eddies occupy. And how we are doing that is getting the Reynolds stress distribution behind in the wake and upstream of the boulder for both relative submergences, and therefore trying to explain here those patterns. the downstream deposition versus the upstream deposition. So this is a bunch of images put together. This is the higher relative submergence condition, and you can see obviously the glass beads, the marbles coming in, depositing in the wake area. In this case here, we got deposition being dominant for the low relative submergence in the stoss. So, in terms of the area, how much difference those eddies can occupy on an average sense? In some cases, close to about 2. So that's a significant error if someone calculates that. So what I have, there is a mistake there. It should be a reversal. The rhomboid shape should be where the rectangular shape. So do eddies therefore contribute? Yes, they do contribute, and in a significant way. So can we incorporate the knowledge that we have about turbulence and near bed turbulence to bed load prediction? I think we are getting closer and closer to develop a practical tool. Another feature that we have looked is obviously how those patches forming around those boulders look like. And we have used fractal theory and the Richardson plots essentially to see how those patches and the dimensionality of those patches changes. And clearly what we have found is that the flow characteristics, where your flow, your mean flow, is highly three-dimensional or two-dimensional, definitely your your dominant fractal dimension is close to 2, but where those patches are almost following a linear path, like a line, then pretty much you are getting a fractal dimension close to 1, a little bit larger than 1. So I'm going to skip that, but those are some nice images from Steve Rice and Annie that we analyzed and looked those patches for them and looking really how the fractal dimension changes. And we looked actually, we did not treat only the fractal dimension in terms of the perimeters, but just the perimeter of the objects, but we looked at also the area that those patches occupy. And you can see really that the two-dimensional shapes right here have a fractal dimension close to about 1.65, 1.7 varies, but closer to 2 versus the one-dimensional features. Mentioned the intermittency, and in all of those experiments we had enough complexity, so I didn't want to add more complexity to it, but some future directions will be really to look at the eddy topology, how that changes as you change the hydrograph and as you change basically your mean flow characteristics, because we have seen before from other experiments clearly the breakup of those clusters, the mobilization, and then the regrouping of those clusters. The last thing that we have been working, and Christian also mentioned that the Lagrangian type of movement is the use of radio frequency IDs into particles, and we're using passive RFIDs because you can penetrate basically through water and sediment bed. And our motivation was essentially to track particles in the flume. So we had more challenges actually tracking particles in a flume than tracking particles in the field, because the magnetic field that the pump generates was interacting actually with your antenna, and it was affecting basically your radio frequency. But we're able to solve this problem. But one of the things that we have tried to do is not only get the number of particles or get the ID of the tags, as we call it, but also try to get essentially the signal strength, the radio signal strength intensity, as we call it, the RSSI, when we send the signal. So how that system works is essentially there is an antenna that excites. So it creates an excitation here to the antenna that is in the tag, in the transponder. And we have used basically transponders from Texas Instruments, but also transponders modified by Texas Instruments, because the Texas Instruments transponders don't have the anti-collision feature. So I'm going to skip some of the stuff, but one thing that we have done is essentially when you get the signal, the radio signal intensity, what we have looked essentially is the voltage that we receive back. And that voltage can be function of a bunch of factors, but pay attention to those Greek letters here, mu. That's the basically the permeability of the material that you are dealing with. So by incorporating that, we're able to collapse our data for different types of rivers: clay, sand, and gravel. The only place that the RFIDs have not worked well is sand, because again, the magnetic field interaction. But it worked very well with gravel bed rivers, and we're able actually to get detection ranges. We are using this type of technology for scour detection, and we can go with about 85% success rate to about 45 feet below the bed surface. So we're talking here for really, changing really from 6 feet to about nearly 60 feet detection ranges. I can give you more information about those transponders. But very quickly, what you see here is when we did not correct the RSSI signal, basically the voltage that gets, and I'm almost there, the voltage that is received, then we have a bunch of lines. But then when we pretty much normalize what, we're making the equation in a dimensionless form, but also incorporating the properties of the material, then the data pretty much collapse along that solid line. So I'm going to stop here, and I'm going to acknowledge actually several people from my group that contributed to this, various aspects of this research. I think you can read on your own the various people there, and the interesting discussions that we had over the years. Thank you.
Thank you, Thanos. So now we're about to start the discussion section. We have about 30 minutes. So I would like to give the floor to Philip Frey, who submitted a question. So in this case, you don't need to mention your name, but for the other people that would like to raise a question, please state your name and also make clear to which of the two speakers you have a question. And maybe the speakers can repeat the question. It might not be clear to the other part of the audience. I'm not sure if there's a microphone for the. Otherwise, okay. Can you bring the microphone to here?
Hello. No. Good morning, everybody. I'm surprised to be the only one. I just do a return on mail. Say, yeah, I'm interested to ask a question. Now I have to think about which question. No, without kidding, I would have a question to both of you about the free surface. I would like Thanos to put your first slide, because it's a very interesting picture about the free surface. Because in gravel bed rivers, and maybe when we have the higher the slope, we have low submergence. And I think this is a complex feature, I think. Just your first slide. I mean, your introduction, because it was a nice picture, okay, of the and this for me, I think that this. So yeah, as you can see, there's a free surface. Okay, we can argue about the word free because I think the surface is not free at all. It is constrained by, you can see, you can see the boulders. Is it a surface anymore? It's quite broken. Okay. And so, the general comment and question is about, we've heard quite complex talks and features about the turbulence, okay, like vortices, Horseshoe, very complex things. But I think that the free surface effect is not modeled sufficiently. Because, of course, obviously, it has an effect on the flow itself. It is part of the flow, okay? But it has also an effect on the segment transport. For example, if you have because you can have, for example, immobile boulders and still be at low submergence and be in stage 3 with lots of sediment transport, rolling or saltating. We cannot distinguish between both, with cobbles also being partly in the flow, partly out of the flow. So, in the perspective of maybe making a minimal model, reduced complexity models, okay, how the free surface come into play. This is from the modeling and also the experimental, from all point of views. I don't know whether I'm clear, but it's free surface effects.
Okay. No, I mean, so it's a huge effect. So the frictional characteristics basically get affected. Also, air entrapment takes place, and that affects your basically Darcy-Weisbach coefficient. Also, with the Freudian wakes that we have seen, when we exceed about 1.2, the Freud number is greater than 1.2 or so, you get two things. You get actually, and André Roy has actually had a paper in France actually, back in Boyer and Roy, 1981 I believe, that he has looked actually for low relative submergence, what's going on, and you see what he called those horseshoe vortices, well-defined horseshoe vortices. In my opinion, they are those von Karman street vortices. So you get actually a very well-defined region in terms of high speed flow. And the other thing also, you mentioned about the depositional patterns, how they get affected. When your wave is standing, then you can see no particles getting trapped actually underneath that standing wave. It's almost getting sacked on the floor of the flume. I will leave the difficult for Christiane.
Thank you. Yeah, excellent question. Actually, in my opinion, when you have a supercritical flow with no significant waves, that's the free surface will not have a significant influence on the sediment transport. Now, when you have large waves or complex things like this, first of all, from the modeling point of view, there's no turbulence model that can deal with this. We don't know how the energy cascade behaves when you have a complex free surface, air entrainment, and things like that. Then, you can estimate some things if you are, I forgot to mention, but there are some methods that are particle-based methods. Some of them are called smooth particle hydrodynamics in which you can simulate very complex free surface in which you have wave breaking and stuff like that. The problem is the smooth part, in which sometimes these kind of models do not yield a very correct turbulence structure below in the water column. So it's a very complex issue, which I think it's something we don't know yet. We don't know how the air entrainment works, how does affect the turbulence. Supercritical flow, it's very, very complex in cases like this. Yeah. So, yeah, I don't know what to say. That's an active research question, an open research question that should make us work harder, I think.
Just to follow up, and then I will finish and give it to other people. One question would be, given the complexity of this free surface, do we need to refine so much turbulence models, or are we able to?
Yeah, the problem is, as I said in my talk, if the scientific questions are related to what Thanos talked about, how turbulence enhances deposition in some areas, or how it enhances entrainment, yeah, I think we can develop sort of simplified models that can give us an idea how this thing works, and yeah, that's I think would be the best way to go. I mean, try to simplify our models in a way in which we assume that some of these aspects that you see there in the picture are not important, and see how we do.
Yeah, if I can say very quickly, I mean, I understand what you are trying to say. Is the surface effect a first order, or, you know, impact effect, and maybe it is. Maybe in this case is, and but maybe by incorporating the effects of turbulence, you know, although one does not counter the other, you know, then maybe you account for those effects indirectly. So this is something to be explored, but maybe those macro features are more important, let's say, in this specific case.
It could be a good way also to combine models, right? If we know that we have a shallow water equation model that can deal with the free surface, then we can use that domain to simulate in 3D and see what kind of structures you have. That would be a first order idea.
Thank you again. I could go on, but lots of people have something to say.
Okay, are there more questions?
James Bathurst, Newcastle University. It's just to follow up on the free surface flow problem, free surface deformity issue to have flow-round boulders. It's more just a comment. There was a study carried out in a laboratory flume, I think in the 1970s, by a group of people, Flammer, Tullis and Mason, which examined the drag on an obstacle, on a hemisphere in the flume as a function of the Froude number and of the relative submergence. And that showed some quite interesting effects as you went up from low subcritical flow towards critical flow and beyond into the supercritical flow. And I've never seen another study like that. I don't know whether others have. I don't know the literature all that well in that area, but it was quite an interesting one for trying to. I think it showed some quite interesting effects for the flow round a boulder, which could be useful for interpreting some of the studies that have subsequently been carried out, and perhaps could be a basis for simulation by these new computational models. Didn't actually involve any turbulence, but it did show the relationship between Froude number and relative submergence.
Yeah, James, that's a good point. There was a study actually by Rockwell from Lehigh in mechanical engineering. That's not exactly, I mean, it was a step, I think, a three-dimensional though shape, but not much, not much. Good point.
Well, going back to that literature might be a useful source for checking your models then.
Right. There's a question. Jeremy? There, yeah.
Yeah, I'm Jeremy Vendetti. I'm from Simon Fraser University. Thanos, I had a question about what the prototype is for your model, for your laboratory experiments. I think I'm familiar with most of the paper you've written on it. And as far as I understand, your shear stress, your non-dimensional shear stress is about 2.5 times the critical non-dimensional shear stress. And so then you're trying to model the formation of clusters where the keystone is supposed to become immobile. And so I'm wondering at 2.5, that seems like it'd be an equal mobility condition, a really high transport stage. And so I'm wondering, how do these simplified experiments translate to the prototype? And I guess more generally, I mean, when you take those simplified experiments and you move them up to a prototype where you have a mixed size sediment, how does it translate?
Yeah. Good question. I get that question many times with glass beads and the simplified, geometry and so on. But just a correction that we are going actually to about 1.25, the tau star critical. So it's 1.25, 1.5, 2, 2.5, all the way to 3.5, basically flats. A caveat there is that how we define also the tau star critical, that we defined it probabilistically. That puts us down comparatively, let's say, to lower value, comparatively to the SEALS parameter. So in many ways, so what I presented here today, I think, is about 1.5. It's a wide range of conditions that we examine. With respect to the simplifications, well, there are a couple of simplifications in terms of also the flat bed. So in terms of the fact that although, as you saw, I became a little bit bolder and I started using different sizes. But different size material, the implications are obviously you have more interlocking. So I am probably more, whatever I am producing there is probably more from the conservation side, meaning more on the lower end than on the higher end, just to give you an idea. But finally, we're transitioning now to real sediment. And so learning from the experiences from others, we got 2 new flumes, Tennessee, that solely devoted for that purpose. So, yeah.
All right. Here's a question, Paul, here in the front.
Thank you. Paul Carling, University of Southampton. This is a question for Thanos. I'll make a couple of observations first. A lot of the previous work on clusters have identified them fairly arbitrary. And in my view, they always appear to be sort of nodes within networks. And you did show some network structure. And whether you're dealing with clusters or boulders, and it's useful that you've put up your title slide, I've never seen real clarification on how these clusters or indeed boulders space themselves out, whether it's obstacles or avoiding the shear zones. They cannot deposit, a moving boulder cannot deposit in the shear zone because of the high stresses, and they manage to space themselves out. Have you looked at the spacing of boulders in particular?
I've looked a little bit at the spacing of boulders in a couple of Idaho streams, and usually those boulders have come down you know, from steep terrains, and in some ways they got some legacy, they got some history, but they came down after a big snow event, and they have been, you know, residing in that stream for some time. Trying to think for real data for spacing, I think probably the Brayshaw study has shown some aspects, but not very systematic data there.
Okay, thanks. Well, you basically confirmed what I thought. I don't think there's very much being done, especially in the field. There are a few very old flume studies by engineers looking at spacing of obstacles that allow flow to pass effectively, and it might be useful to go back to some of those.
Mm-hmm. Yes, and very briefly, we've looked isolated because that's very simple, but the Jaeger study actually has looked at different packing densities, and you found actually, Bill, that had a huge impact. In some ways, you form another paved layer, so to speak, because material gets deposited there. So that's another thing in the books that we're going to look. Thanks, Paul.
All right, so there was a question over there.
Jens Dorowski, German Research Center for Geosciences. So I got a question which is quite nicely illustrated by your photograph, and that is the role or the effects of air entrainment. And this is a topic you always see that in steep streams, and as steeper the stream becomes, as more important it seems to get. But I'm not aware of much work on the effects of flow velocity and on sediment transport, bedload transport specifically. So my question to you is do you have any insights into that, and how would you incorporate that into models, both the simple ones and the complex ones?
You mean any insights from field work, or and velocity parameters, or bedload, or both?
Well, any insights you might have, I don't know. I'm only aware of some engineering work in terms of engineering structures of ramps and things like that from the 1980s. Hubert Chanson did some work on that, but I'm not aware of any work done in natural rivers on the effect of air entrainment.
Yeah, very, very little information when it comes to low relative submergences due to the difficulties in making those measurements. And for example, a person that spent a lot of time making measurements is Alan Wall, those type of measurements in those, kind of rugged type of environments, and some others. But very, very little information. That's the reason I think that lab work at this stage, maybe it's a good way. I wish that ADCPs, and we got a couple of people here in the room with more knowledge on ADCPs than I have, could work in those shallow depths, but they don't. And also the disturbance again with airflow. So people have used large-scale particle image velocimetry, looking only the free surface characteristics, but they don't give us much. Only you can make some assumptions that the log law is valid, and that's not the case, or at least it's not fully the case. So hopefully the lab work for that condition can give us a little bit more insight how we can go about and how we can become smarter to go out and maybe make those measurements and use, let's say, probably I will go to SAFO and try to do that probably in a more controlled environment, and then go to the next step, next level of difficulty. So good point, though.
Christian, would you like to add something on the difficulties of modeling?
I was just remembering, well, if you have something like, if you want to simulate our air entrainment with volume of fluid or a very sophisticated it ends up with a very expensive calculation, which is really also at lower Reynolds numbers. But in that case, you have to simulate both fluids and try to track the interfaces and the bubble entrainment. But again, without any detailed measurements, it's difficult to validate and simulate. Thank you.
There may be some insights from the community modeling waves, air entrainment in waves.
Yeah, not my area of expertise, but I've seen that the simulations turn out to be very expensive all the time that they try to simulate that kind of things. Yeah, I think that there have been some simulations of hydraulic jams, and they have been able to reproduce some characteristics, but again, it's difficult to validate them if you don't have high resolution measurements.
All right, any more questions? Let's move to the back a little bit.
How far back?
Okay, it's the final question.
Oh, me, okay. Thank you, Colin Rennie, University of Ottawa in Canada. The question, I have one for Thanos, but I'll save that for later. Question for Christian. Mm-hmm. I was interested in the paper by Kang and the LES versus URANS results.
Yep.
I've done some similar work in bends, modeling bends, and one thing that we found was, yes, the LES resolved the three-dimensional structures much better, but sometimes the bulk flow velocity at a single location, on average, was better predicted by a RANS model. And that's because the three-dimensional vortices, or secondary flow features, were not always in the exact correct location. And I'm wondering if you've had similar results, and I guess broaden the discussion, if that's the case, which is the better one for predicting sediment transport or bank erosion? Because really you want to get the shear at the right place at the right time.
Yeah. Again, this is my opinion. Well, there are two things. First, when you have a highly resolved LES, you probably need a lot of time to make your variables converge. Right? Since you have so much variability, you need at least to know that if your processes are stationary, you need a long time series to have convergence. So sometimes you can have problems like that your simulation is not long enough and you have a lot of data to process that you haven't really converged to the average. And this is again my opinion, when you have even though it's RANS and it looks like in terms of the average velocity looks better, when you need to know the distribution of shear stress and you don't have the correct structures that exist in the field or in nature, it's really difficult to say that RANS is better. But now, and that's the other point of view, if you want to look at time scales that are long and in which the effect of these vortices is not persistent enough to leave an imprint on the larger scale structure, you're probably well off with a simpler calculation. What bothers me is that you're using an isotropic turbulence model for a very anisotropic flow, which is wrong from the start, right? So if you want to keep it low cost and resolve the topology of the flow, I would go with some Reynolds stress transport, a more advanced version of RANS that can resolve the anisotropy, and you don't have to do LES in that case.
All right, thank you very much. This is the end of session 1. I would like to ask you to return to the room by 11 o'clock. And I would like to thank the two speakers and all the discussants from the audience.
Okay, thank you, Astrid. Well, before the coffee break, I would like to ask you several things. One thing is that in your bag, you will find this file. And inside of the file, you will find several documents. And these two documents